Hi, guys. Okay, so let's look at some of the examples that relate to the hybridizations of Sp3, Sp2, and Sp, and how to draw those structures. In the previous video, we covered the introduction, so I just want to quickly review it here in the steps to make the hybrid structures. So first of all, you will start with counting the total number of valence electrons, and you will count and you will make the Lewis structure. Next, you're going to count the number of sigma and the pi bonds in the Lewis structure. Then you're going to look at the electron groups. Then you're going to match the electron groups with the hybridization type. After that, every hybridization, basically, you make those, they're just the lobes. With the hybridized orbitals are shown as lobes. So you make those lobes for each atom. Okay, and then after that, you're going to make the sigma bonds first. In other words, you're going to do the lateral overlap of the hybridized orbitals. Then you're going to do the sideways overlap, which is the pi bonds, which is the, if there is a double bond or the triple bond, then you would need that. Then you just make sure that you have counted all the, valence electrons, and they should account for in the hybridized structure also. Just keep this in mind that when we look at the shape, we look at the electron group geometry of that. So now let's just do a little review of the details that we cover. And I have this all in the handout. So here is this handout, which is posted in the modules, but the electron groups. Electron groups are also called the effective pairs in some of the books. So basically, lone pair, a single bond, a double bond, and a triple bond, all of them constitute as one electron group. So if there are two double bonds, there's going to be two electron groups. If there's one triple bond and one single bond, then it will be two electron groups. So you see, the triple bond is considered to be one electron group. Okay, so that's one piece. Next is these electron groups. They relate to the hybridization, and then each hybridized each hybridized orbital has a certain shape, and that particular atom will have that shape with these orbitals. Okay, I mean the orbitals, hybridized orbitals will have a shape. Okay, anyway, so here we look at these two electron groups. If there are two electron groups, then it will be Sp hybridized, and the shape is going to be linear. If there are three electron groups in the Lewis structure you identified, then it is going to be Sp2 hybridization, and it will be trigonal planar. 4 electron groups, Sp3 hybridization, tetrahedral shape. 5 electron groups, Sp3 hybridization, trigonal bipyramidal. 6 electron groups, Sp3d2 hybridization, and the shape is octahedral. Also, keep in mind that these lobes, when you make the hybridized, orbitals, just make sure that you also have the lobes done correctly. So for Sp hybridization, only 2 lobes. Sp2 hybridization, 3 lobes. Sp3 hybridization, 4 lobes. Sp3d hybridization, 5 lobes. And Sp3d2 hybridization is 6 lobes. Now, if you're wondering what are these 6 lobes and what is this Sp3d2, I recommend that you look at the previous video in which there is an introduction to the hybridization, and I've specifically explained in the energy diagrams where the orbitals are mixing. So the specific orbitals, whatever the number, so S and one of S and one of P, when they mix, they only make Sp hybridized orbitals, and so we show that as 2 lobes. If one of S and 2 of P orbitals mix, 3 lobes. If one of S and 3 of P's mix, 4 lobes. If one of S, 3 of P's, and 1 of D orbitals mix, 5 lobes. If one of S, 3 of P's, and 2 of D's mix, then it is 6 lobes. Okay, so that's the deal with the lobes. The next comes the sigma bond. Now, sigma bond, remember, single bond is one sigma bond. A double bond contains 1 sigma bond and 1 pi bond. A triple bond contains one sigma bond and two pi bonds. Okay, so sigma bond is always formed first when we draw the hybridization structures. Then the sigma bond is always drawn first. I mean, all the atoms that they're connected by a single bond first, and then later on we do the sideways overlap, which is the pi bond. And we already covered these energy diagrams. So like I said, this is your handout, which I have posted in the modules, and you can, print it out and use it if you need it. So here is now, we are going to look at the specific examples. So let us look at now here. Let me just move here a little bit like this. Okay. All right, let's look at, first of all, Sp3 hybridization. And in this one, we are going to look at, first of all, methane, carbon with 4 hydrogens. All right, so as the steps we indicated, first of all, total valence electrons. So total valence electrons are, for one carbon is bringing in 4 electrons, and we have 4 hydrogens, each bringing 1 electron. So we are looking at a total of 8 electrons, 4 from carbons, and then 4 coming from 4 hydrogens. Okay, so 8 electrons total. That's one piece. Next is, let's draw the Lewis structure. Carbon makes 4 bonds, hydrogen makes only 1 bond, so carbon goes in the middle. So here is this carbon, and we have these 4 hydrogens connected to carbon in a tetrahedral fashion. Okay, now here is the Lewis dot structure of carbon, and if you look at the octet of carbon is met. Hydrogen doesn't follow the octet, but hydrogen has 2 electrons, which is good. Now here's a few things I want to discuss here. I'm not going to do this for all the molecules, but let's look at, in this case, specifically with carbon, and how this sp3 came into being, and understand that. So first of all, carbon has 6 electrons, okay, a total. So the Lewis dot, so the electronic configuration is 1s2, 2s2, and 2p2. Okay, now the orbital diagrams for 2s2 and 2p2 looks like this. So let's place these. So 2s2 is this one, and 2p2 is first you singly occupied. Now here's the deal. If you look at the electronic configuration, carbon only is showing 2 unpaired electrons. So 2 unpaired electrons means that it can only make 2 bonds, right? Because these 2 atoms, because these 2 electrons need to be paired, and right now they are not paired, but once they get paired, they're going to form pairing. What is pairing? Pairing is basically making bonds. So pairing of electrons is what is called bonding. So let me put this here. Bonding. Okay. Bonding is basically pairing of electrons. So we should see only carbon making 2 bonds, but carbon makes 4 bonds all the time. So what's going on here? So in the case of carbon, now here's the thing. Here's the, sorry, I'm not going to use a different color here. Here. So this is the energy diagram. And in this energy diagrams, as you see, here is the 2s2 and here is the 2p. And there are 2 electrons here, and there are 1 electron in each of the 2p's. So 2p. Now what happens is that this electron, which is with 2s, jumps and comes here. How do I show this? Jumps, one of them jumps and comes here. And when that happens, this is called the internal jumping. Internal jumping. Okay. Now, when that happens, then all these S and P orbitals, they begin to mix. The P lowers its energy, the S raises its energy a little bit, and a set of new orbitals forms, which is Sp3, and all four of them have the same energy. So one of the S has mixed, and the other is one of the S mixed, and the three of the P's mixed. And each of them had now 1, 2, 3, and 4 electrons. So this is how this electrons basically, they spread out between S and P, and they have, each of them have their own orbitals, lower in energy state than the P and a little bit higher than the S, but more stable. Okay, so how do they look like? They look like this. So here is this one. So this is the carbon in the middle, and all of them around the carbon, they are in this tetrahedral fashion, all of them. Okay, and where is the electron? Electron is here. One electron here, one is here, one is here, and the other is here. So each of the hybridized, so each hybridized orbital is like, you know, let's put it in this other color, has a little bit of the S character, but a very broad P. It has, the P is like very big, thick. So normally, you know, you have the P's very thin like that. That's the PX. This is the PX. This is one of, let's do this. Okay, here is the, these are the, okay, so as you can see, the S orbitals, spherical, the PX, the PY, and the PZ, they're small, thin lobes. And when they mix, they make the Sp3 hybridized orbitals, which are, you know, which are thicker and like bigger. So in other words, they would contain 75% of P character. That is why the lobe is like more like flatter or bigger, and 25% is the S character. So even the S is like a little bit small. So this is the actual hybridized, you know, Sp3 hybridized orbital. Okay, so that's the deal with carbon. Now let's look at how, you know, they make the bonds now. Okay, so here, as you can see, when the electron internally jump, they make the Sp3 hybridized orbitals, and each of the hybridized orbitals contain one electron. And now comes the hydrogen. Hydrogen is bringing in 1s1. You know, that's the orbital of hydrogen, 1s, and that 1s contains only one electron. And so this one electron, and hydrogen, because its S is just spherical, so you know, it doesn't matter, but similar, but since it's a sigma bond, so it's still going to be a horizontal side, you know, lateral overlap. So this orbital overlaps with this hydrogen 1s1. This one overlaps with this hydrogen's 1s1. This Sp3 hybridized orbital overlaps with this hydrogen's 1s1. And here this one, Sp3 hybridized orbitals, overlaps with the hydrogen 1s1. Okay, so this way, these are 4 sigma bonds are formed. In other words, it's a lateral overlap, and it's just a single bond, or in other words, 4 single bonds are formed. Okay, so here also, like we said, look at the Lewis structure and then count the sigma bond. So this is 1 sigma bond, 2nd sigma bond, 3rd sigma bond, and 4th sigma bond. Okay, so that's 4 sigma bonds are, you know, shown in the, this is the, basically this is the energy diagrams. Now you don't have to draw it all the time, but I just wanted you to see how the electrons, they overlap, you know, internally. Now let's draw the structure. How does it look like? So first thing is that you're going to put carbon here in the middle. Okay, and now just keep this in mind that although, we drew this, which color is that? This one. This one, actually, the S is at the back, a little bit at the back right here. So you don't see it. It's like, it's because it's like a balloon, that little piece of the balloon, it's kind of hidden. That's why. But just keep that in mind that it is there. Okay. Excuse me. Here is this thicker lobe. These are the Sp3 hybridized orbitals of carbon. And just make sure that you are drawing them in the tetrahedral shape. Tetrahedral shape. Okay. Why tetrahedral shape? You would know, it's from here. It also, we were here. If you look at the electron groups, there are 4 electron groups. 4 electron groups are these 4 sigma bonds. Okay, or in other words, 4 single bonds. And these 4 single bonds relate to 4 electron groups. And we know that these 4 electron groups are going to, if you look at your chart here, the 4 electron groups relate to Sp3 hybridization, and the shape is tetrahedral right here. 4 electron groups, not 5, but 4 relate to Sp3 hybridization, and the shape is tetrahedral. Okay, so this is something, you have to eventually memorize that relationship, but that's what it is. Okay, so that's where the tetrahedral is coming from. Okay, next is you are just going to place the hydrogens 1, 2, 3, and 4. Okay, so this is hydrogens 1s1. This is hydrogens 1s1, hydrogen 1s1, hydrogen 1s1. Okay, now let's put the electrons, and I'm going to put it with this color. So this is the 1 electron of carbon and 1 electron of hydrogen. This is 1 electron of carbon, 1 electron of hydrogen, 1 electron of carbon, 1 of hydrogen, 1 electron of carbon, and 1 of hydrogen. So this is these 2 electrons. Remember that single bond involves the use of 2 electrons. Okay, so that's 1 sigma bond here. This is 1 sigma bond. This one is 1 sigma bond, and this one is 1 sigma bond. Okay, so the 4 sigma bonds are shown in this way. Okay, now tetrahedral geometry is also, now besides this, the shape is tetrahedral. We also covered, one second, where is that? Okay, so this is another handout we have. So here we see that the molecule or the ion type, A stands for the central atom, and X stands for the outer atoms, and E stands for the lone pair on the central atom. So we see that, or the atom that is in question. Okay, so here we see that it is AX4 type. AX4 type means A is a central atom and it's connected to 4 atoms. Now, total number of electron groups, we already calculated that, those were 4. Then the number of bonding electron groups, in other words, the number of bonding atoms, or how many atoms it's bonded to, bonded atoms are 4. Then number of non-bonding electron groups, or in other words, are there any lone pairs? So no lone pairs on the central atom on carbon, 0. Then the electron group geometry is tetrahedral. The molecular geometry is from outside. Electron group geometry is from inside. Okay, internally. So internally tetrahedral, externally tetrahedral, and then the angle is 109.5. Okay, so tetrahedral electron group geometry. Oh, electron group geometry. Okay, and then the molecular geometry also is the same. Molecular geometry is also tetrahedral. Okay, so both the thing, electron group and the molecular, both of them have the same shape. Okay, so that's the deal with the sp3. Now let's look at sp2. Okay, so now we are going to look at the example of C2H4 in sp2. Now here what happens? Here we see, as usual, that the electron on the carbons is going to jump from the S to the P. Okay, and when that happens, now we have a singly occupied S and the P orbitals. But now this is one step. But next, how many are mixing and what's happening here? So only the mixing is between the S and P, two of P's. So only these are going to mix. Only one of S and two of P's mix. So I don't want to confuse this. Only S and 2P mix. And when they mix, what do they form? They form sp2. And when they form sp2, just keep that in mind, that sp2 would be a lower energy state than the P's. That's one piece. Now, there is another thing that did not mix. So this P does not mix. These two mix, but does this P does not mix. And as a result, this P remains as a pure P. So this P would be this is a pure P, okay, or it is unhybridized. This is another unhybridized, term they use, which is not mixed. Okay, hold on. Okay, so now let's look at the sp2 contains a singly occupied, like these three singly occupied orbitals, right, of sp2, and the P, pure P, now will still contain that one electron that had jumped. So what happens is that the pure P is holding to that one electron, and the remaining three that mixed, they formed an Sp2 hybridized orbitals. And now we have carbon looking like this. So carbon will have these three, Sp2, remember that, three lobes. Sp2, these relate to three lobes. So where are the carbons here? So where are the electrons? One electron here, another electron here, and another electron here. So this is the Sp2 hybridized carbon looking like this. Okay, and it's a trigonal planar. So remember we talked about a pizza, a shape of a pizza. So trigonal planar. That's the shape. Okay. Now let's look at the shapes. Now, first of all, in C, now I'm going to make this small. Now, C2H4, let's count the total number of valence electrons and so forth. So we have 2 of carbons and we have 4 of hydrogens. Carbon is bringing in 4 electrons. Hydrogen is bringing 1 electron. And we have here, for 2 are 8 electrons are coming from carbon, and 4 electrons are C2H4, 4 electrons coming from hydrogens, so a total of 12 electrons. Okay. And now carbon makes the maximum number of bonds, hydrogen only makes 1 bond, carbon makes 4. So obviously the Lewis structure is carbon is going to be in the middle, another carbon comes this side, 1 hydrogen is here, another hydrogen here, another hydrogen here, and another hydrogen here. So connect them first with the single bond, and that uses up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and then carbons, you check the usual Lewis structures. You check whether the carbon its octet is met or not, and whether its need to make the bonds is satisfied or not. So now with this structure, carbon is making 4 bonds, carbon's octet is met, hydrogen doesn't follow the octet, but hydrogen is making single bond and hydrogen has 2 electrons. Now sharing, after sharing. So this way, all the 12 electrons have been accounted for. So that's one piece. Now, next thing, according to our rules was, after you draw the Lewis structure, you are going to look for the count the sigma and the pi bond and look at the electron group. So let's do that first. So we have here, after this we have 1, 2, 3, 4, 5. There are 5 sigma bonds. Okay, so that's one thing. And there is 1 pi bond. Okay, so this is a sigma bond. This is a sigma bond, right? This is a sigma bond. And this is a sigma bond. And where's the pi bond? Where's the pi bond? Pi bond is on the top. This one is a pi bond. Okay, so that's one piece. Next is the electron groups. How many electron groups there are? So if you look at it, there are electron groups. So between carbon and hydrogens on both the sides, there are 4. And then between carbon and carbon, the double bond is considered to be 1 electron group. So a total on each carbon, on 1 carbon, there is actually 1, 2, 3 electron groups. So between carbons, let's write this down here. Between, let me put this properly. Okay, so between the 2 carbons, there is the double bond, which is considered to be just 1 electron group. But between the 2 hydrogens and the carbons, and then, between carbon and carbon, so all this overall, keeping carbon as a center. If we just keep carbon as a center here, we see that carbon is surrounded by 3 electron groups. Those 3 electron groups on carbon relate to what kind of hybridization? So if you look at the hybridization on if there are 3 electron groups, so it is the Sp2 hybridization, and that is trigonal planar. So let's go back here. So this is trigonal planar. Trigonal planar means like a shape of a pizza. So in other words, it's basically, see, these are just electron clouds, right? So the shape of that electron cloud. So if this is a carbon here, then between hydrogen and this hydrogen, so it's like that piece that it's like a triangular cloudy region like that. Okay, so now we are going to make our structure. So let's put carbon here, 1 carbon here in the middle and another carbon here, and let's bring in the Sp2. Remember, Sp2 is let me change this. Sp2 is this one was Sp2 was triangular, 3 sides. So 1 side here, this one is here, and this is here. Okay, now comes the other one. Let me change this one. This here, this one, and this one. So now the hydrogens. So 1 hydrogen, another hydrogen, another hydrogen, and another hydrogen. So you see every carbon in 1 minute. Okay, so now let's put the electrons. So 1 hydrogen is bringing in 1 electron. The other, the color is, let's put a white color. This might be easier. Okay, 1 hydrogen bringing in 1 electron, and this is remember, these in the end, they have 1 electrons over here on the carbon, right? So here, every carbon has 1 electron on this lobe, and the hydrogen is bringing in 1 electron. Here, 1 electron, from carbon and the other electron from the other carbon. One electron from carbon, another from hydrogen. One electron from carbon, another from hydrogen. So if you look at it, a total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons have been used. And these are what? These are the sigma bonds. This is one sigma bond, another sigma bond, third sigma bond, fourth one, and the fifth one. So we already counted 5 sigma bonds here, 5 sigma bonds. So these are our original sigma bonds that we formed by the flat overlap. Okay, so let's just put this here. This is hydrogens 1s1, hydrogen 1s1, hydrogen 1s1, and this is another hydrogen 1s1. Okay, and then those are the 2 carbons. So that's one piece. Now remember, there are a total of 12 electrons, and we have only accounted for the sigma bonds, but we haven't looked at the pi bond yet. And we have this pure P still holding that 1 electron. So how do we show that one? So here is this pure P. Let's get this in a totally different color right here. So 1, 2. So, you know, this way, on these 2 lobes, we will have the only 1 electron. So you can draw either up or you can draw either up or down. It doesn't matter. Whichever side you draw, just make sure that you show the overlap, you know, that side. So these 2 guys are forming the bond, and that bond is the pi bond. So this is the sideways overlap, and that is the pi bond. Okay, so that is the part double bond. So you see now 12 electrons total have been accounted for. So 12 electrons have been used. 2 are in making the pi bonds, which is a part of the double bond, and the remaining are all in single bond, sigma bonds making. Okay, so that is the main, you know, thing. But just keep this in mind that if you are making the pi bond on the top, don't touch the bottom part. If you're making the pi bond at the bottom part, don't touch the bottom part. And each of the lobes can only have, you know, only 1 electron can be found. And if 1 electron is in one lobe, the other lobe has to be empty. So you can, you know, roll it that way. So basically that's the deal with the C2H4 sp2. And I hope that, you know, the electron geometry with respect to carbon, is trigonal planar. Okay, now let's look at sp. Okay, same story with sp. Sp. Okay, sp, we are looking at the C2H2. So here is C2H2. Okay, so here we have the same thing. In this case, let's show, just want to show you the energy diagram. So here is the energy diagram. So what's happening here is the S, this is the 2S, these are the 2 P's. And in this case, you find, you know, this guy has 1 electron. Now I'm just going to make it like this, and, or should I just do the same thing? Okay, anyways, just for the sake of maintaining a continuity here, this one jumps, and now you have another scenario where you have these singly occupied orbitals, and we have 1, 2, 3, and 4. Okay, now what's happening here? In this case, 1 and 2 mix. So S and P mix, right? And then what happens when S and P mix? Now we have new orbitals, which are S and P are here. So this is the sp orbital, and sp orbital still has this one electron and one electron. That's fine. However, now we have two pure P's. These guys have not mixed and they remain where they are. Their energy levels are still higher and they are still holding one electron. Okay, so now we have, when we talk about sp, that means that carbon will have one lobe here and another lobe here. And then where are the electrons? The electrons are present. One is having here and the other is here. So it's going to be making bonds on both the sides. All right. So these guys remain as pure P's. So let's put this here. These do not mix, and hence these two remain as pure P. And that means they're going to be overlapping on the side. So, you know, this we draw, of course, the initially when we draw the sp hybridized carbon, we show only the two lobes, but the P's are still present. It's just not drawn here. They are still present. Okay, so now let's look at their structures. So as the thing, carbon, one carbon, and then, so let's draw the total number of valence electrons and the Lewis structure. So C2H2 means that two carbons are bringing in 4 electrons and 2 hydrogens are bringing in 1 electron. And here we have 2 4s are 8 electrons here and 2 electrons here. So we are looking at a total of 6 electrons. Okay, 6 electrons. All right, that's one thing. Now let's draw the Lewis structure. So C and C, because carbon makes the most bond, so it gets the center spot. And we have 2 hydrogens, one on this side and on other on this side, because hydrogen only makes 1 bond. So connect them with a single bond. So we have used 1, 2, 3, 4, 5, 6. 6 electrons. 1 second. 2 4s are 8. Oh, 8 plus 2. I'm sorry. It will be 10. That's what I'm sorry. It will be 10. 10 electrons. Sorry, that's what I was. Okay, anyway, so here 1, 2, 3, 4, 5, 6 we have used, and carbon makes 4 bonds. So it is going to now accommodate the remaining 4 electrons. Okay, so this is how carbon makes 4 bonds. Hydrogen makes only 1 bond. Hydrogen has 2 electrons. Carbon has octet. Very satisfied situation. Now let's look at the sigma bond. So this is 1 sigma bond. This is another sigma bond. And this is the 3rd sigma bond. So there are 3 sigma bonds. And this is 1 pi. And this is another one. Another pi, 2nd pi. So there are 2 pi bonds and there are 3 sigma bonds total in this. Okay, so that's one thing. Now, how many electron groups there are? There are on each carbon. On this carbon, there are 2 on, you know, on both, basically both the carbons are the same. So both the carbons are the same. So 2 electron groups each carbon has. Okay, on both the sides. So when we have 2 electron groups, what does it relate to? 2 electron groups. 2 electron groups relate to sp hybridization, and that is a linear shape. It should be spelling linear. Anyway, so now we have, this means that 2 electron groups is equal to sp hybridization, and that is, the shape is a linear shape. Okay, now let's draw it. All right, so I'm just letting you know up front that, you know, this type of overlapping, generally if we are, you know, looking at test question. Okay, something similar, not exactly the same question. Okay, anyway, so here is one carbon and this is another carbon, and it is bringing, this guy is bringing its one lobe here, another lobe here, and the second one is bringing one lobe here and another lobe here. Okay, and there is one electron this carbon has. This carbon has one electron. This one is bringing its one electron and one electron, this carbon, this side. Okay, so this is one sigma bond carbon has formed by this overlap. Next is carbon is going to combine with hydrogen. So this is the hydrogen bringing in its, it should be small, but hydrogens, 1s1 of hydrogen, and this is hydrogen 1s1. Okay, and here we have so that is one electron of hydrogen, and that is overlapping, or the 1s1 orbital is overlapping with the sp hybridized orbital of carbon, and that's how the two electrons are being shared, and they're forming a sigma bond. And here this one, this is the sigma bond. Okay, and then we have the sigma bond at the bottom. Now we have the sigma bonds, the 3 sigma bonds. Now we need to look at the 2 pi bonds. Now keep this in mind that let's get this one. Okay, px is thin, and anyway, px got used up. Px got used up, but py and pz are thin. So keep that in mind. This is thin. This is thin. Okay, and this is containing only one electron. One electron. Okay. Remember that this is this one electron from the pure P, these pure P's, the ones that did not participate in hybridization. So they only have one electron. Okay, so one electron, and now we have another one, which is, let's see, let's get this one. Okay, here one. Remember, PZ is diagonal. This is another one, PZ. So this one is the PY, this is PZ, PY and PZ. Okay, and PX participated. But PZ is also containing one electron. So right here is one. Let me put it on the other side. Okay, maybe not. Yeah, this is okay. And here, okay, so this is the PZ. Now you are just going to connect them to show that they are forming this bond. So just remember that if you are doing the Z, if you're doing the X, no, sorry, the Y and the Y are going to be, overlapping, and you can show the overlap like this, and this is the other overlap. So this is the pi, and this is the pi. Okay, so if you're showing on the top, don't show at the bottom. If you're showing at the bottom, so just make sure that it's only one-sided. All right, and so we have now, if you look at it, a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons have been accounted for. Okay, 10 electrons have been used up. And carbons is, we can see the sigma bonds, we can see the pi bonds between the carbons, and we can see the hydrogens with the hydrogens also. Okay, so that's the deal. And since it's a linear, the shape is a linear shape. Okay, so that's the SP, SP2, and SP3. And now we're going to look at the other examples in the next video. Thank you for watching. Bye-bye.